Pretty much everything in the universe is made out of matter. The Earth, air, you and me, stars, interstellar dust, all matter. By which we mean that these things are made out of electrons and quarks, and very occasionally other rarer matter particles like muons, tauons, and neutrinos. All of these particles are, at their fundamental level, excitations in everywhere permeating quantum fields. But as the famous quote goes, for every particle, there is an equal and opposite antiparticle, an opposite excitation in the everywhere permeating quantum field that has all of the exact same properties as that particle, except opposite charge. And since these antiparticles are opposite excitations of the quantum field, when a particle and antiparticle meet, they annihilate and destroy each other. Which is pretty much exactly like how the equation x squared equals 4 has two solutions, 2 and minus 2, with the same value but opposite sign, and when they meet, they annihilate. Every fundamental particle has an antiparticle. There are anti-quarks, anti-neutrinos, anti-muons, anti-tauons, and of course anti-electrons, though we call them positrons. Since antimatter particles are essentially identical to regular matter, other than the opposite charge thing, they can combine together in essentially identical ways to form antiprotons, anti-atoms, anti-molecules, and in principle anything from anti-ants to anti-Matterhorns. We can also make the really cool positronium atom. It's like hydrogen, except instead of an electron orbiting a proton, it's an electron orbiting a positron, until they annihilate each other in under a nanosecond. Because every particle of antimatter annihilates with regular matter upon meeting, it's really hard to make anything big out of antimatter. At this point, we're still only able to make and contain a few hundred anti-hydrogen atoms at one time. And when a particle and antiparticle annihilate, the energy has to go somewhere, which is why matter-antimatter annihilations have been proposed as bombs. But naturally occurring antimatter is hard to come by. So unlike a uranium fission bomb, which allows us to release the bottled energy of the supernovas that forged the uranium in the first place, you'd have to put all the energy into an antimatter bomb yourself by making antimatter, which you do by agitating empty space into pairs of matter and antimatter excitations. Kind of like hitting 0 with a hammer to get out 2 and minus 2, except instead of a hammer, you use a particle accelerator or high-energy photons of light. Photons, incidentally, have 0 charge and so are their own antiparticles, in the same way that 0 is equal to -0. In fact, mathematics has always been closely tied to antimatter. The mathematics of relativistic quantum mechanics predicted the existence of antimatter for years before any had ever been discovered. The fact that there's so little antimatter around in the universe to discover is both an obvious thing, because if it were around it would have destroyed us, a good thing, because it can't destroy us, and a puzzling thing. If matter and antimatter are basically identical mirror images of one another, why did the Big Bang produce so much more matter than antimatter? No one knows, but to physicists, the answer matters. Hey, this is Henry. Thanks for watching this video. It was brought to you by Audible.com. Audible is a leading provider of audiobooks across all types of literature, including fiction, nonfiction, and periodicals. Today I'd like to recommend Stuff Matters by Mark Miodnik. It's a great book about, well, it's not about antimatter, but it's about stuff that's made out of regular matter, stuff like steel, glass, plastic, and even chocolate, about the material properties and stuff. It's a great little read. If you go to audible.com/minutephysics, you get a free trial and a free audiobook of your choice, and it really helps out the show as well. So thank you for watching, thanks for supporting us, and go to audible.com/minutephysics.